Welcome. Thank you for joining the talk today. My name is Sam George. I'm a director on Azure IoT. Been around the IoT space for quite some time now. For those that have been following, we've been in market now for several years. And we're here today to talk about one of our newest innovations, what we call Azure IoT Edge. This actually follows a big set of announcements that we did over the last couple weeks that I'll just recap very briefly. We announced a new upcoming IoT SaaS offering called Microsoft IoT Central. We announced Azure Time Series Insights, which is now available in public preview. We announced a new Azure IoT Suite pre-configured solution called Connected Factory. We also announced some great out-of-the-box support from Windows IoT Core for our new device provisioning service, which we also announced, the IoT Hub device provisioning service for enabling provisioning at scale. We announced some new security partnerships. So there's a whole bunch of things that we've been announcing, but we were holding back on IoT Edge for this event for a bunch of reasons. And what we wanted to do today, this morning, if you were in the keynote, you saw that I did a demo with Sandvik Coromant. And I showed how you can take some intelligence in the cloud and run it on small little IoT devices. Today we're going to give you much more detail about what exactly we've built and are still building. And we're going to talk about how it works, show you demos. We're also going to talk about what's coming next and roadmap and things like that. We'll also have time for questions and answers. It shouldn't take, the slide parts of this won't take the entire time. So with that, I thought it would be worth framing, and it's worth thinking about what we mean by edge and where this fits in the grand scheme of what we refer to as waves of innovation. When you look at the world of technology, there's these waves that always stack on each other. And for us, IoT is just another wave of innovation, and so is edge. So cloud is obviously a well-established wave of innovation, globally available, unlimited compute resources that you can spin up without having to go buy computers. Built on that is IoT. And IoT in this context we're defining as being able to harness signals from the real world in real time or near real time, and then to take actions on those. I'm always fond of saying that there's three parts of an IoT solution. There's the things, which are not always the devices. A lot of times it's what the things are monitoring, be it elevators, be it industrial metal cutting machines, be it cows, be it dogs. Those are all real. It's often the things that you're interested in and not the devices. The devices are a means to an end. There's the insights that you gain from those things, and then there's the actions that you take as a result. And then, of course, there's a whole bunch of details about each one of those and what you have to do to benefit from that. But IoT, I think at this point, is a pretty well-established pattern. And really what's happening now is that there's several new waves that are stacking up on top of it. The one that we're talking about today is Edge, which I define as taking an IoT device, which at the time was simply sending signals and receiving commands for things like device management, and starting to put more and more intelligence down on them. We realized very early on in our journey in IoT that there was going to be a balance between the cloud and the edge of the network on the physical world. Because if you think about the billions of devices that are getting connected and the trillions of messages that they send, it just makes sense to be able to do a bunch of pre-processing out on the edge before that data is sent to the cloud. And then there's a whole bunch of things you can do with local intelligence that are really more optimized for devices. And part of what's happening with this, like Satya mentioned in the keynote this morning, is there's the reality that as more and more data is generated and collected by these IoT devices, data has gravity. And so you have two choices. You can lift it up and move it to the cloud, or you can just move compute down to it. So that's really sort of the broader context of what's going on. And the other wave that's happening at the same time as Edge is AI. And so part of why we're doing Azure IoT Edge is exactly what I showed in that keynote, where you're able to take cloud intelligence. You don't have to custom develop intelligence for the edge. You can simply move it out to the devices. But it's also a platform that enables AI services to run locally as well. And so we have all of this in mind as we're bringing Azure IoT Edge to market. like I mentioned, there's that balance between the edge and the cloud. There's some things cloud is very, very good for, which is collecting and aggregating data from all over the planet. You saw Scott talk about the 38 regions that were available in worldwide. So, we have these hyperscale capabilities, these data centers, and collecting that data and then using it in aggregate to train machine learning modules and AI is an important use of the cloud, and also to be able to manage the edge. And then, of course, there's a need for the edge. When you start talking about low latency needs or needing to develop something that runs on a physical device so that if there's a network interruption, it keeps running. And also, there's customers with concerns around data protection and IP. And frankly, this is part of why we're doing not just Azure IoT Edge, but also Azure Stack. One of the questions you might have that I'll just head off now is how Azure Stack and how Azure IoT Edge relate to one another. And the way that we're building both is that they will work just the same. Like you'll be able to use Azure IoT Edge along with Azure or with Azure Stack. And I'll explain that in a little more detail. But there's a very nice plan between those three offerings. The other thing I'd like to do for a second is step back and think about, there's a bunch of different requirements when you start thinking about processing on the edge. If you think about a X and Y axis where the Y axis is reliability requirements, some things you need to be very, very, very redundant and high availability. Some things you don't. And sometimes you have significant needs for custom code. So there's this X and Y axis, and that forms a little bit of how we think about Azure IoT Edge and the kinds of sophisticated features that we build for it. So the first quick stop to evaluate is when you have a low need for custom code, but there's different reliability requirements. So let's say in the lower left-hand corner, you're just doing some batch data processing locally, right? If the process dies and you restart it and it just picks up where it left off, great. If you get to the point where you're doing something a little more high reliability, like business logic, where you're executing almost transactional code, then you definitely want this to be high availability, high reliability. And for that, part of the capability that we're building into Azure IoT Edge is the ability to work on redundant nodes, right? So that it can do failover and load balancing. Along the medium custom code requirements, you start seeing a whole bunch of the things like what I demoed this morning with Sandvik Coromant, industrial IoT adapters. Part of what you do on these edge devices is protocol adaptation. IoT and M2M have been around for a long time, with a different name. And there's a lot of protocols out there that you frankly wouldn't want to stream over the open internet, many of which have security vulnerabilities. But they're fine for talking to a local device and doing protocol translation there. And so a big use we see for edge computing is around protocol translation, data normalization, simple batching and workflow. And things like that are high reliability needs. Smart protocol or smart building protocol translation is another good example. And so what I'm doing here is I'm showing not just the custom code versus reliability requirements, but also some of the scenarios that fall into that. And then, my personal favorite to talk about edge computing is sort of what pushes the envelope right now. If you think about autonomous driving, the way that works is that you take volumes of data plus all sorts of sensor inputs that were simulated on the car, referred to as sensor fusion. You take that and you train deep neural networks against video of road, all sorts of environmental signals, and what you come up with is some very sophisticated deep neural networks that you then package and deploy right on the car itself. Now the car doesn't have a cloud loop running while it's connected, while it's driving. If someone jumps out in front of your car, there's no call to the cloud that decides whether or not to stop the car. That's very obvious. But it is logging telemetry to the car for improvements. And a lot of times what will happen is when the car gets parked somewhere, it offloads its very, very copious data that it's been collecting, which is then used to retrain that. And so you can start to see there's this balance between the edge and the cloud that are circular. Along the same lines of this custom code requirements, what you see is there's different hardware requirements. So part of what we're doing with Azure IoT Edge is building it so that it can run on a big variety of hardware. From very, very low constrained devices, single CPU, 128 megabytes of memory, all the way up to multi-device blades. What I'm showing here is a couple things. I'm actually going to clarify it in a few slides. When you look at the world of IoT devices, there's a bunch of different capabilities, all the way from very tiny sensors, which make up a large part of that 20 billion devices that is predicted to be connected by 2020, all the way into very sophisticated high-end multi-blade gateway deployments. And we have an internal notion that we talk about a tiering of these things. And so this is really showing everything from a single CPU, 128 megabytes of memory, all the way up to very sophisticated gateways. And there's a variety of workloads that'll get pushed out to the edge. And there's a life cycle that you have to manage for each of those. Because it's not just about getting the intelligence out there. Once you have it out there, you also have to manage it. You have to update it. You have to configure it. There's a lot of times, in fact, when once you have intelligence running out on the edge, you don't need to update the code. You just need to update configuration. So that's part of the plan as well. The goal here is to enable Microsoft services that are relevant at the edge to run on the edge. And there were some great examples that we showed this morning, from machine learning to stream analytics and even cognitive services, Azure functions. Those will be among the first. And making it so that all of them can compose together and that you can control them and manage them. And then also making it so that you can declaratively be able to control what functionality should run out with which, or with what configuration, and then to have our systems then goal seek and achieve that configuration. This makes it all of this makes it possible to manage the edge and take advantage of this balance between the cloud and the edge. And so for everything from simple processing all the way through complex processing, we see the need for this out on the edge between the cloud. So some of the highlights that when we talk about Azure IoT Edge and some of the design goals that we had and the things that we're enabling with it, the first is secure. So part of it is Azure IoT Edge is managed by Azure IoT Hub. It uses a connection from Azure IoT Hub, which is secure two-way, high-volume communication between the two, to establish a communication, to establish identity, to manage, to push out workloads and configuration. The second, like I mentioned, is it's cloud managed, and so we will actually mirror the state, which I'll talk about in just a second. We'll mirror the state of what the device is doing, including all the workloads that are running on it in the cloud, so that you can control it there. Very importantly, it's cross-platform, so it will support Windows 10 IoT Core. It also supports multiple versions of Linux, and will support all the popular versions that support containers, because Azure IoT Edge, one of the fundamental building blocks is containers, which I'll talk about in just a second. Portable, this is an important point. One of the things I mentioned in the keynote this morning is that a very important part of this symmetry between cloud and edge and the ability to move workloads between it, if you think about what's next is you want to be able to mock your entire edge deployment in the cloud. You want to be able to run your CI/CD pipelines in the cloud. And then on successful deployments, then to simply deploy containers and configuration out to the edge, right? So that's what we're enabling with this. And then finally, extensible. This has to be able to be used by third parties or by third-party services. So it was one of the reasons why we chose Docker-compatible containers, so that anything that can run in a Docker-compatible container, you'll be able to deploy out to devices that are capable of running that thing, including your own code. So in the example of an autonomous car, if you had your own custom-built deep neural network and Azure IoT Edge was running on a chip that had a specialized ASIC chip, you would be able to deploy a container that could take advantage of that. All right, so that's the high level. Just some high level framing about why and what it is. Let's take a little bit of a deeper look and then we'll get to a demo. So at a deeper look, let's just talk about what a high level topology for an IoT solution looks like. So it's actually a little more than this, but it's a good place to start. So here I'm showing Azure with a customer solution. The customer solution is using Azure IoT Hub to do the connectivity, the two-way connectivity between devices in the cloud. Within that customer solution box, there's actually a whole bunch of little boxes that I'm not going to show, which could be everything from storage to analytics to business process integration. There's a bunch of little boxes there. But I want to talk about the edge right now. So some of these devices talk directly to Azure IoT Hub. And so sometimes you just have an IoT device that's just acting like an IoT device. It's just sending telemetry, it's receiving commands, you're managing it, there's nothing super special that's happening there. Sometimes you'll be running Azure IoT Edge out on a device, right? Where you're able to then push logic down to it and program it from the cloud and deploy your logic down there. And oftentimes what you'll see is devices that are connected to Azure IoT Edge, and then those devices can be managed by Azure IoT Edge as well. And part of what we're enabling with Azure IoT Edge and our device management capabilities in Azure IoT Hub is to be able to manage not just the Azure IoT Edge device, but also the devices behind it in a secure and reliable and scalable fashion. Does that make sense? Because if you think about a lot of what Azure IoT Edge will be used for is gateway scenarios, where you're actually managing a fleet of devices behind it, and that gateway is providing perhaps security isolation for all of those less capable devices. That's a typical topology that you see in IoT. All right, so before we get into the details of Azure IoT Edge, I wanted to spend just a minute talking about how Azure IoT Hub device management works, because Azure IoT Edge is built on that. And so last November, we introduced some new concepts in Azure IoT Hub, specifically some device management primitives, and then some software built on top of that for doing different protocols. So it's worth explaining that because the next slides will make more sense after that. These are already available, and one of the things I should point out is that, at the time, we had customers live in production, obviously worldwide, and when we added these device management capabilities, we updated all of the IoT hubs worldwide with zero downtime. So these new features just show up, right? And you wake up the next day and we tell you, hey, there's a new SDK and you can use these things. And you only pay for them if you're using them and things like that. But you don't have to, take all your devices and migrate to a different IoT hub or anything crazy like that. We do things in a forward compatible way. And you can just keep using the IoT hub, and then when you're ready to take advantage of those capabilities, you can. So before we introduce this, there were two channels. If you ignore in IoT hub, if you ignore all the device identity, device registration, things like that, concepts, there were really two channels. There was a telemetry channel for sending telemetry, and telemetry, just to be clear, is fast-moving data, for example, temperature and humidity, something that's changing, and that's often being delivered in a time series fashion. And then commands, being able to initiate a cloud-to-device command. What we introduced last November was a notion of device twins. And what a device twin is it's a state synchronization mechanism between devices and the cloud. And the way it works is it's a two-way communication. Now, there's a set of properties that are used in the device twin. The first is desired properties. So each one of these properties is just a property value, name value pair collection. And it's just JSON with JSON data types. So desired properties, and the whole idea behind desired properties is that they're owned by the cloud and replicated to the device. So the device gets updates from the cloud, from IoT Hub on desired property state changes, but it can't change them locally. The cloud owns those. Then there's reported properties, which the device owns, and it can make changes to them all day, and those are replicated to the cloud, but they're read-only in the cloud. And using these two property collections, we can communicate back and forth between devices, and I'll give you an example in a second. The last property collection is a cloud-only collection, which is called tags. And tags is intended for grouping. So let's say, for example, that we have a bunch of IoT devices in this hall, and there's some in the next hall over. If I want to identify all of these and be able to query for them later, I would simply add tags that these are all for Hall C, for example. So an example of using device management with these properties is I would set desired properties to tell the device, hey, your update window is between this time. Here's your firmware URI that you're going to download. Here's any configuration I want to push to you. And then I would push that down to the cloud automatically pushes that down to the device. The device, in turn, just responds by setting a reported property that signals acknowledged. I've got that information. Then within that update window, it simply download the firmware, reinstall, and then set a reported property to indicate the either success or failure of that. And using this mechanism, you can coordinate virtually any change between devices in the cloud. One of the things that's really important about this is that we batch all of this. So for example, if the device is offline and you write a bunch of reported properties, they all get, or desired properties, they all get stored. And then when the device reconnects, then it'll initiate a synchronization with it. And then finally, there's methods, which is the ability from the cloud to send a request response to the client. And so you can send a request and get a response code back immediately. So an example of where you would use this is to be able to dump diagnostic information, for example. You could send a request to say, give me all of your, or set error condition, or set logging level 2, and then all of a sudden open up the telemetry channel. And another important part of IoT Hub device management is two more concepts. Number one is jobs, and the other is queries. What jobs are, actually I should talk about queries first. What queries are is the ability to query across any of the device twin property collections. So you can query across reported, desired, tags. So for example, if I was about to perform device management in this hall, I would query for all devices in hall 6, and get back a device twin collection. Then I could create a job, and what the job does is then go set desired property changes or tags, or even call methods. And the reason why we call it a job is because it's a long-running process. And so, it's not just one device typically that's being operated on, it's millions or billions of devices. And so being able to run a job and being able to have that long-running process managed by us, and then also being able to query the job to find out where is it along the way, how many devices have completed, and so on. All right, so that's enough about Azure IoT device management. So let's talk about Azure IoT Edge based on what I just told you. So the first is some highlights on it. Number one is it's based on containers. It's based on Docker containers, Docker compatible containers, which both Windows can run as well as multiple versions of Linux. And so the operating systems that we'll support as part of Azure IoT Edge will all support Docker compatible containers. Azure Functions, Stream Analytics, Machine Learning, and Cognitive Services are all supported. So we made an announcement 2 weeks ago that Azure Stream Analytics is now going to target edge devices, specifically Azure IoT Edge devices. So let me explain a little bit about how that works. Today, for those of you that have used Stream Analytics, it's a nice, really compact, complex event processing system where you can simply write queries using SQL, and it's got some extensions for things like tumbling windows. So you can do queries like, hey, for the last, for a 5-minute sliding window, take all the telemetry that I've seen from these certain fields, score them against this machine learning module, and if the probability is greater than 80% of a schedule adjustment for the maintenance window, then alert me. And you can do all that in about 20 lines of SQL. It's pretty amazing. So the whole idea behind Stream Analytics on the edge then is you'll be able to, in Stream Analytics in the portal, say export this to a container. And then that container will be able to be deployed through IoT Hub down to an Azure IoT Edge device. All right. We support offline synchronized device twins for not only the Azure IoT Edge device, but you'll see in a second the functionality that's running on it, as well as devices that are connected to it. And so if you're doing some local processing and you wanted to reason over what's happening to a device connected to Azure IoT Edge, you could consult its local offline device twin. So even if the network's down, you can still do that. We already talked about cloud management and deployment. We also have local storage for store and forward so that you can batch up telemetry in the case of offline and then send it when you get back online. We're also building in high availability and fault tolerance, so you'll be able to have multiple of these devices and failovers and be able to fail over with load balancing. And then a really important part of it, and I like to stress this, is the cloud dev test support, being able to develop in the cloud and mock the device in the cloud, and then to be able to deploy down to the device. All right, so let's look at some of the intrinsics. So the first thing that Azure IoT Edge has is a device twin for that device. Now, using this device twin, you can manage not only the workloads that you're going to be putting down on the Azure IoT Edge devices, but also the device itself. So if you want to update software, firmware configuration, this is the device twin that you use. The next capability is local storage. We also have the functions runtime, so the ability to execute functions once they've been exported into containers and deployed down to Azure IoT Edge. And then finally, basic container management, being able to place and heal containers. On top of that, each of these services will support exporting to Docker-compatible containers and running on an Azure IoT Edge device. Now, the important part is this. We have a new concept that we're introducing along with Azure IoT Edge, which is something we call module twins. And what module twins are is they are, anytime you deploy a container down to Azure IoT Edge, you will also get a module twin. And what a module twin is, it controls the configuration of that container. And so if there's state that you want to pass along with that container, and you want to have that module, or you want to have that the code in that container pick it up, it will have access to the module twin and changes to the module twin. And then same thing in the cloud. So for example, let's say that you pushed an Azure function down to Azure IoT Edge, and you wanted to change how it behaved on subsequent executions. You could simply alter its module twin. You can think of that as almost like passing in command line arguments, and change that in the cloud, and it'll replicate down to the Azure IoT Edge device to control that workload. So a lot of what you can do with this, let me just talk about some of the scenarios. So I already talked about protocol translation. The demo that I showed this morning with Sandvik, which we're going to talk about here in a second, or show you in detail, that's really about, hey, we're going to listen, we're going to have some container listen on a network socket to the device itself. Then we're going to use Azure Stream Analytics to reason over the data coming off of that. We can score it against a machine learning module to determine whether or not the maintenance window needs to get adjusted or the device needs to get shut down. And then we can also have an Azure function that can trigger that shutdown. And we also have a container that we'll include with Azure IoT Edge for communicating with IoT Hub back and forth. There's a lot of other scenarios. One of the things you saw this morning was the AI for workplace safety. So you can imagine another scenario for Azure IoT Edge where you're listening to a video stream, you're taking that video stream and pumping it through a cognitive service. The cognitive service is looking for faces, and instead of then streaming video to the cloud, you're simply sending faces to the cloud. As an example, if you were recognizing people. When we talk about the different devices, we refer to these as device tiers, everything from sensor tiers to constrained tiers. Azure IoT Edge is really geared towards what we refer to as interactive tier and above, which is really 128 megabytes of memory, single CPU, and above, all the way up through industrial and gateway tiers. And so it'll be available to run on all of these. And with that, we're going to get to the demo part of our talk. So I'd like to welcome up Raj Vengali. Come on up, Raj.
All right. Give me just a second here. All right.
And then which out do you need?
Yeah, we can, no, actually, this is good. This is good. Thank you, Sam. Hello, everyone. My name is Raj. I work as a developer on the Azure IoT Edge team. And I'm here to do a quick demo of the Azure IoT Edge runtime to kind of showcase some of the things that Sam talked about, how you can use the Edge runtime to remotely deploy, manage, and monitor software components on your IoT Edge device. So this demo is kind of based on roughly the same scenario that you saw in the keynote that Sam showed this morning. That is based on an actual customer scenario, Sandvik in this case. when I did trial runs of this demo, for my team internally, one of the feedback that I got was that there's just so much going on in this demo that I'm kind of finding it difficult to follow along what's happening. So before I get into the demo, I wanted to take a minute to kind of explain the outline of the demo to you. What exactly are the sequence of steps that you're going to see in the demo, and then we will get into the demo itself. So to begin with, essentially, the box at the bottom left, the edge device, represents the edge device. We will have what is called as the module management agent or an update agent running on the edge device. This agent is responsible for essentially managing the lifetime of the software components that are deployed to the edge device itself. In this case, these components are managed by Docker, right? So these are Docker containers. These are images that get pulled from a container registry. They get deployed, and they get started up, and the management agent essentially manages its lifetime, monitors its health, communicates that back to the IoT hub. So that's the essential role of this edge device. One thing that I want to point out here is the choice of Docker as a technology for this management is basically implemented in the Edge runtime using a provider model. What that means is we are able to swap out Docker with an alternative container management technology, right? So for example, conceivably on Windows 10 IoT Core, you might see all of these management capabilities being implemented using Windows 10 IoT Core's device management functionality. In this demo, though, we're going to use Docker containers. The first thing that we will see in the demo is an IoT hub module being deployed to the edge device. So what is this edge hub module? This is essentially a local version of the IoT hub. It provides essentially the same services that its cloud counterpart does. It accepts, you can send telemetry to it. You can route messages through the Edge Hub module. So it's a router, it's a broker, it's a message broker running on the edge. So you could say that the Edge Hub module is probably the one non-optional module on the Edge runtime, because that essentially enables communication between the modules and between the module and the cloud, right? So that's kind of the heart of the Edge runtime. And in the demo, you will also see a module being deployed which is responsible for communicating with a machine, right? So in this case, it's going to be a simulated machine, but in the real world, you would have this module communicate with an actual machine, read telemetry from it, and be able to control the machine. That's essentially the hardware interface. And then we would, one of the things that we frequently find customers talking to us about is, how do we do more on the edge, right? Like, I don't want to simply take all of the telemetry that's being generated by all of my machines and sensors all the way up to the cloud. Maybe I want to do some aggregation on the edge and then take the result of that aggregation and push it up to the cloud. How do you do that? So we have in the cloud Azure Stream Analytics, right, ASA. A couple of weeks, or maybe last week, a preview of this was announced where you're able now to use Stream Analytics on the edge, right? You're able to use exactly the same queries and essentially run them on the edge. So in the demo, you will see an ASA module being deployed to the edge as well. In this case, in the demo, it runs a query which computes an average of RPM data over a moving 5-second window. So a slightly non-trivial query, right? And then that output gets routed all the way back up to the cloud. And then you will find that there are other scenarios that we want to enable from the edge. What happens if a machine begins to malfunction, right? You really don't want to incur the latency of, you could detect that that malfunction from the cloud and then send a cloud to device command and cause that machine to shut down or to essentially take some action. But there are latencies involved when you're talking about going all the way up to the cloud. In fact, that's what you saw in the keynote demo this morning, where you found that when you deployed your components onto the edge, you found the latency dropping dramatically. So one of the things that's going to enable this scenario is machine learning. So what we did was to create a machine learning model in Azure Cloud We trained the model, and then we got it packaged as a Docker container, and then we're pushing it down to Azure Edge. In the demo, the ML module is responsible for analyzing the data that the sensor is producing, and then detect if a failure is imminent, and if yes, then send a message to the local hub instructing that that machine should be shut down. And then we will go ahead and deploy an Azure function module whose role here is to essentially send the instruction to shut down the machine. The goal here is to kind of showcase that it is possible to take an Azure function definition from the cloud and package it and deploy it as a module on the Edge runtime. So you can kind of see an overall theme here where we're able to take services that are running in the cloud, and we're able to package them and deploy them onto the Edge runtime. So this kind of plays to the scenario where, as a developer, you want to be able to develop, debug, test all of your code in the cloud, and then be able to, with minimal effort, take all of that and package it and deploy it on the Edge runtime. And also, as another scenario, we'll see how we can essentially update the software. Right? That's a pretty common scenario. You have done something, you've shipped it out, it's running in production, and you discover that there is new functionality to be had, and then you build it, and how do you deploy that using the same infrastructure where you're essentially replacing a module? So that's the demo outline. So all of this we wanted to show you running on a Raspberry Pi with all of these modules deployed. But we discovered about half an hour before the talk that there is no internet connectivity from the Raspberry Pi at all. Therefore, we are not going to use the Raspberry Pi, but to prove that we actually did all the work, maybe this will work. All right, so we got a document camera, and here's the Pi. As everybody knows, any self-respecting IoT demo has to make LEDs blink, right? Unfortunately, we are not going to be able to make LEDs blink because there is no connectivity. Don't worry, though. At the right time in the demo, I will ask you to close your eyes and imagine an LED blinking, and that's what we will do. All right. Excellent. So what I have here is, so I'm running the entire demo on my laptop. So I have Docker installed here, and I have the Edge runtime installed here. What I will do is go ahead and open a web portal. So another probably thing that I should mention is that all of this is, what you're seeing is essentially bleeding edge bits. This is like a developer build of all of this. So you will see JSON files, you will see command shells, you will see developer UI like this. Not very pretty, but the idea is to kind of showcase all of the scenarios that we spoke about in the outline. To begin with, I want to go ahead and deploy an initial set of modules, including the IoT Hub local module, the Edge Hub. So as Sam mentioned, how all of this is working is using the device management primitives that IoT Hub supports, right? Device twin, device properties, device method calls. So essentially what we're doing is the edge device itself is represented in IoT Hub as a device and as a managed device, right? So when we say we're deploying a set of modules to that device, what we're doing is we are updating that device twin's properties in the cloud with the configuration of the modules. And that update gets propagated to the edge device through our IoT SDK, and then it starts executing those steps. So as a first step, I want to, let me just move this over here. So this is a definition of, this is exactly the patch, the device twin patch that we're going to be sending for the first deployment, right? So this, every entry here describes a module. So for example, this is my IoT Hub local module. And since we're using Docker as the technology for managing all of these modules, essentially what we give here is the image name for that module that is to be deployed. You will notice here that I'm using Azure Container Registry for pulling the image. So the Edge Runtime's Docker implementation will support using your own custom image registries. And then there are these other configuration options here to describe, for example, what port it needs to export. The IoT Hub local implementation here uses exports an MQTT head. Therefore, it has a port binding for 188.3. I'm cheating a little bit and also deploying the ML server ahead of time because ML server, it's actually the Azure ML implementation. It takes a little bit of time to get started up. So while I go with the rest of these steps in the demo, this module will get deployed as well. So I'm going to go ahead and copy this and deploy it to our Edge module. So essentially all I'm doing is specifying what patch needs to be sent to that device, and I go ahead and hit send. So essentially what's happening here is the web application, which is running on Azure. So you can see it here, maybe. So this is running on Azure websites. So essentially what's happening is the web application is issuing a device method call, I think every second or so, to the twin of the Edge device in IoT Hub. It's requesting, give me a list of modules that are running on the Edge. And IoT Hub forwards that request to the Edge device, and the Edge device responds with a list of modules that it is running, and then it gets routed all the way back to the web application, and then we display that over here. So the next step, if you remember the outline, is to deploy the device sensor module, right? The module which is essentially simulating the device that's simulating the software component that's communicating with the device. So let's take a look at the JSON for the device simulator. All right. So here's the JSON for the device simulator. So essentially, very similar to the IoT Hub local one, we just pull a different image. I know what happened earlier. I picked the wrong JSON. So I had kept all of the JSON files open, ready, so that I can just send them. If you notice the name of the file up there, maybe you cannot see it, it's py-up.json. So this is fully Py images. So that's what happened just now. All right, so here is the device simulator. If you actually look at the device simulator for the Pi, you will notice that there's more configuration here. For example, I specified that we need to volume mount the sys/sys/GPIO path into the container. This is because that's how we are able to blink LEDs, because that's really important. But the idea here is that we are able to actually access hardware from within Docker containers. But of course, when we are running it on my laptop, we will use a different configuration which does not do that. Therefore, let's go back to our web portal. I'll paste the device simulator. So the device simulator has started. Essentially what the simulator module is now doing is it's generating some telemetry at random, and it is pushing it up to the cloud. Now, I mentioned that there is a router. So the router that is running on the IoT Hub local module, let me just zoom in there. I think it's probably not visible to people all the way at the back. So the IoT Hub local module is receiving telemetry from the device sensor. And we have configured the router on the IoT Hub local to forward some of that traffic, in fact, all of that traffic, to the IoT Hub in the cloud. So that's what is happening. And this chart that you're seeing here, the time series chart, is essentially reading the telemetry from the cloud, right? So this is running on Azure, and it is reading the telemetry from the cloud, coming from the Edge device, routed through IoT Hub local. So the next step in the outline is to essentially deploy an ASA module. So let's take a look at what that looks like. So this is the JSON for the analyzer. Doesn't look very different. This is the query that I'm running on the ASA module. So in this case, I'm saying basically pick the average of the RPM as this particular column using a tumbling window of 5 seconds, grouped by that 5-second window and the name of the machine. So you can see this is a SQL-like syntax that you can use to essentially define your ASA query, right? This is the exact same query that you use in ASA on the cloud. So what we have done is we have taken this, compiled it to the ASA representation, packaged into a container, and we're going to deploy that to the edge device. So go ahead and deploy that. So the analyzer starts running. It's been deployed. If you look at the console here, you'll see that the container analyzer has started running. So this analyzer is essentially receiving, again, just like the device simulator, this is basically receiving all of the data from the device sensor, and for every piece of data, it's essentially computing that moving average, and it is uploading that information, again, through the IoT Hub local to the cloud. All right. Then we spoke about, so another thing that the IoT Edge runtime allows us to do is essentially, we saw how we can deploy a module, but how about, you determine that maybe at some point you want to take down a module, right? What does that look like? So since we're using the device management primitives of IoT Hub, we're able to essentially use a JSON like that. This looks like a pretty simple JSON, right? All I say is assign null as the value for a particular module, and we interpret that as an instruction to remove that module. So let's see what that looks like. I'll go ahead and deploy that. We should see that the container for the analyzer got removed, and we no longer see uptime and CPU percentage showing up for that particular module. Next, let's go ahead and deploy our ML module. So, whoops. So that's our anomaly detector module. In this case, what this does is this module essentially communicates with the prepackaged ML server, and again, for every piece of telemetry that's coming from the device sensor, it sends that data to the ML server. The ML server scores that piece of data, saying whether it's essentially a Boolean flag that it returns, saying whether it's likely that this machine will fail or it will not fail. And then based on that output, we need to take some action. And for that, we have an Azure function. So essentially, this is the JSON that we're going to send for the module that's going to take the action based on the ML module's output. And here you can see that the function itself is loaded from an Azure blob storage, right? So essentially, this is the mechanism that allows us to kind of change what function is going to run at runtime. So I'll go ahead and deploy this module. To show you that we also have a CLI interface, I'll deploy this using the CLI. So this is the machine shutoff JSON. It's the exact same JSON. Except that instead of doing it through the web, I'm deploying it through CLI. So there's the machine shutoff module that just showed up. So now all of the modules that we want running on this edge device are running. Now, for the sake of the demo, we want to see what happens if a particular machine starts malfunctioning. So what I will do is simulate an error by running a little script. So essentially, I have, 3 machines here, machine 0, machine 1, and machine 2. I'll go ahead and cause machine 1 to fail. So I'll go ahead and run that little script there. What it did is it essentially used essentially a sidecar port on my device simulator and instructs it to generate data that will cause the machine learning module to report that this machine is going to fail. So actually, a lot of things happened just now. You can see that the RPM on the machine, went to 0. If I look at the log for the device simulator, you will see that this is the point where you should imagine an LED going on and off. It's a poor man's LED there. So essentially, in the real demo with the Pi, you would have seen that the green LED would have been blinking. But essentially, to signify that the following happened. As soon as I ran that little shell script, it sent a request to the device simulator This is purely for the purpose of the demo. In the real world, the machine would have actually generated that data, right? It would have said that the machine is going to fail. The device simulator generated the data that, in this case, I know what data it is that will cause the machine learning module to report that it's going to fail. The machine learning module detected that it's going to fail. It sent a message to the function module. The function module caused the device simulator to shut down that machine. And shutting down the machine in this case means that it stops generating telemetry, right? There's no more RPM being generated. So for the final piece of the demo, what I want to show you is how can we ship different functionality. So I have this. As you can see, it is essentially toggling the power to pin 18 on the GPIO pin 18 on the Pi. I have here another module that I call machine shutoff alarm. Essentially, it's the exact same module with the exact same name, except that it's a different function, right? So instead of shutoff.zip, I have shutoff with alarm.zip. So I'll go ahead and deploy that. So you can see that the machine shutoff module just got taken down, and then it got brought back up again. If you look at the console, you would have seen that it did the same thing. It turned it down and brought it back up again. So what I will do is, in order to reset this, I will reset the trigger for that. So now this will cause the device, the machine 1, to come back alive, essentially. So you should, in a few seconds, start seeing some data coming up for machine 1. So there's machine 1 back in action again. You will see that the graph looks a little weird now. It's like it goes all the way to the top and flattens out. And the reason for that is because of the scale of the data, right? So for a long time, the data was 0, and now it's back to sending the usual amount for the RPM. Therefore, it's trying to fit all of that data in that same space. Therefore, it goes all the way to the top. But the data is still, randomly fluctuating. What I will do now is go ahead and cause a failure. So I will run my trigger fail again, and time for you to imagine the other LEDs blinking. So essentially, the function now sent a different signal, right? It caused the device simulator to say, basically sent a different message to the device simulator, and the device simulator responded to that by essentially interfacing with a different GPIO port. The takeaway here, though, is that we were able to essentially ship different functionality completely remotely, right? We were able to, essentially using a different JSON and a different URL to the function definition, we were able to replace the functionality of the edge device. And as you can see, the machine got turned off as well. With that, we come to the end of the demo. I hope it made sense. Sorry about the little snafu here. Thank you.